What's left behind when a massive star collapses at the end of its life? In particular, when the core is massive enough that it can overcome electron degeneracy pressure, so the endpoint is not a white dwarf. The disruptive explosion leading to a supernova in principle could detonate the entire material, obliterating the star and sending it all into space and leaving nothing behind. That's one possible outcome, but more likely, in terms of theoretical calculations, is that a compressed state of matter will be left behind, far eclipsing the density of a white dwarf. If the core is more than about 1.5 times the mass of the Sun, but less than about 3 times the mass of the Sun, the new collapsed state, consisting of pure neutron material, because the protons and electrons have coalesced in a reverse version of the beta decay process, the pure neutron material will be supported by neutron degeneracy pressure. The fact that neutrons are unable to occupy exactly the same quantum states, as predicted by Fermi. This is a standard part of quantum theory, so although neutron matter may sound very exotic, its physical properties are relatively well understood. So, in this situation, where the core is more massive than a white dwarf, it will collapse to the state equivalent to a large atomic nucleus, with an atomic number of 10 to the power 54, a phenomenal state of matter. You can almost imagine the neutrons sitting next to each other, like grains of sand touching, or eggs in an egg box. The density of matter is the same as the density of matter in the atomic nucleus, 1 trillion grams per cubic centimeter. In this situation, a star more massive than the Sun has squashed, by gravity, to a diameter of 10 or 20 kilometers, the size of a small city. As the star collapses, it entrains magnetic field, trapping it within the plasma. And just as by conservation of energy, the star must heat up when it collapses, the star also must increase the density of its magnetic field lines as it collapses, and they're squeezed in the shrinking plasma. So in principle, a collapsed stellar remnant will have a phenomenally high magnetic field. By conservation of angular momentum, the spin rate will also increase dramatically, so the object may be spinning much faster than it was as a normal main sequence star. The properties of these objects, called neutron stars, were predicted in the 1930s. Much of the work was done by Robert Oppenheimer, who went on later to become the architect of the Manhattan Project, and then suffered an ugly end to his career when he was blacklisted for political reasons and banned from doing government-sponsored research. Oppenheimer was a brilliant theorist, one of the best in physics of the last century. This was an era before computers. All his calculations on the state of neutron stars were done with pure mathematics and physics. He predicted that there should be stars situated in space with a density equivalent to that of an atomic nucleus, spinning perhaps as fast as 1 or more times per second, and with magnetic fields trillions of times more than the magnetic field of the Earth. The Earth's magnetic field is about 1 Gauss. For comparison, a refrigerator magnet is about 100 Gauss, and a sunspot is threaded by a magnetic field of about 1,000 Gauss. White dwarf is a fairly compact state of a star, but its magnetic field is about 1,000,000 Gauss. Neutron star magnetic fields are 1,000,000 times larger, several trillion Gauss. For several decades, the idea and prediction of neutron stars just sat in the literature. There was no way to test it. How could you possibly see a tiny remnant of a star emitting no energy, no obvious way of detecting it? In fact, observers essentially dismissed the prediction of neutron stars as some esoteric piece of theory that couldn't possibly be tested. We flash forward 30 years to the University of Cambridge, where a young graduate student, Jocelyn Bell, is taking radio observations of several regions of the sky, trying to map out radio sources. As she's observing with this early radio antenna, she observes a radio source in the constellation Vulpecula. Unlike most radio sources, it's pulsing, and when she checks it against the standard atomic clock that they have access to, she's amazed to discover that it's a more precise timekeeping object than the atomic clock itself. The radio trace of the pulse shows that the intensity varies from one pulse to the next, but the period is absolutely lock-steady. It's an astronomical metronome more accurate than 1 part in a trillion. She talked to her research advisor, Tony Hewish, and they puzzled over this. They called it a pulsar, but they had no idea what it was. In fact, the regularity of the pulses was so confusing that they jokingly referred to the first few found as LGM1, LGM2, LGM3, meaning little green men. The supposition being that only an intelligent civilization far beyond Earth could generate radio signals with this accurate a frequency. Jocelyn Bell followed a classic scientific method pursuing her discovery, As the number of pulsars found with that radio telescope increased, she tracked down and ruled out alternative sources of the emission. In particular, since the sources rose and set 4 minutes earlier each day, it's clear that they were keeping sidereal, or star time, rather than terrestrial time. But she went further, ruling out other possible sources of radio emission, such as faulty alternators on nearby cars or other radio equipment in nearby villages. Eventually, she and her advisor were convinced that they discovered something important, but they were still puzzled as to what it might be. Then Tony Hewish, her advisor, made the connection with the long-forgotten papers in the theoretical literature on the prediction of neutron stars. Here could be a star rotating that rapidly in a collapsed state. Were pulsars the long sought-after and speculated neutron stars? The answer turns out to be yes. In particular, it's now thought that most neutron stars are indeed completely invisible and emit no radiation of any kind. But a small set of neutron stars have imperfections on their crust where at the surface cyclotron emission is generated. This is the low-frequency radiation resulting from electrons spiraling in the intense magnetic field of the neutron star. This radio emission, resulting from electrons near the surface of the neutron star, emerges on hot spots on the crust of the neutron star. And because the star is spinning, those hot spots project their radiation like a beam into space that pivots around the sky with the rotation frequency of the neutron star itself. So, as was realized in 1967, pulsars are the subset of neutron stars where there's radio emission from the surface, cyclotron emission where the beam goes into space and as the star rotates, sweeps across the Earth to be detected by radio telescopes. The pulsing is therefore sequentially the beam passing over the Earth time after time as the star rotates. And because the star is so dense and small, it rotates rapidly, so the pulses are quite frequent. Radio catalogs now contain 3,000 or more pulsars, mostly in the plane of the Milky Way galaxy, and most within distances of hundreds of light years of the Earth. Every now and then a pulsar is found where the cyclotron emission extends to higher frequencies and is visible optically. There's only a handful of them, but they include the most famous pulsar of all, the pulsar at the center of the Crab Nebula, the dying star that detonated in 1054 AD. This pulsar has a period of exactly a third of a second and has been observed pulsing in optical light as well as in radio waves. In this picture and then animation of the Crab Nebula, we see the neutron star at the center. The surrounding region is the detritus from the supernova that went off a millennium ago, and X-ray telescopes such as the Chandra Observatory show that gas glowing and actually changing its structure from year to year because of the changes in density as the radiation passes through the interstellar medium. It's worth taking a moment to let settle in exactly how exotic and bizarre a neutron star is. A neutron star is an entire star the size of the Sun, 1 million kilometers, that's collapsed to the size of a city, that has a magnetic field trillions of times that of the Earth, and is spinning hundreds of times per minute. Pulsars with a wide range of frequencies have now been detected. The early pulsars mostly had periods within a second and about 1/10 of a second. The longest pulsars are rarely more than a few seconds in period. The most rapid pulsars are called millisecond pulsars because their spin rates are hundreds of times a second. Let's listen to a sonification of 3 different pulsars. This is the trace of the radio waves literally turned into a sound wave so that you can hear the frequency of the pulse passing over the Earth as the neutron star and pulsar spin. The first example is a long period pulsar with a period of about 1.4 seconds, sounding more or less like a metronome. The second is a fairly rapid pulsar, revolving at 33 revolutions per second, a period of about 30 milliseconds. The third example is one of the most rapid pulsars known. It's going so fast that it emits a whine above middle C on the piano. Again, this is an object the mass of a star and the size of a city spinning 600 times per second in space. Neutron stars have been studied in sufficient numbers and in enough detail to produce other interesting science. Indirect detection of gravity waves was shown when a binary pulsar had its period slowly increasing. Energy loss in the binary system, and the spin-down rate of the pulsars matched exactly the prediction from general relativity of the release of unseen gravity waves from the system. Pulsars are brilliant timekeeping pieces, accurate in the best cases to 1 part in 10 to the 15. They're nature's best clocks, but they're not perfect. Occasionally the stresses in the spinning neutron material adjust or alter the crust in a form of starquake unique to neutron stars. In a neutron starquake, the strength of the pulses and their frequency changes abruptly to form a new situation as the crust rearranges. This has been observed a number of times. There's also a very slow but steady and detectable spin-down rate in most pulsars caused by the release of gravity waves. In another bizarre consequence that's a prediction of general relativity, if we were able to stare at a neutron star, we'd see more than half of its surface, because light is bent so much close to the neutron star that it passes round the backside, meaning we can see behind the half of the surface we'd expect to see. As a last piece of pulsar exotica, consider this. To be correct, historically, the first exoplanets to be discovered were not 51 Peg and its neighbors in 1995. The first exoplanets discovered were found in 1992, orbiting a pulsar. As the discoverers are happy to point out, the first planets were not found in 1995. The pulsar 1257+12 had slight irregularities in its timing, which were used to infer the presence of planets. The exquisite precision of the pulsar as a metronome allowed these deviations to be modeled as planets, not just a planet the size of the Earth, but even a planet the size of the Moon. It's likely that these planets were not given as much attention as they should have been because nobody expected planets to be formed around the pulsar, and nobody could imagine how there might be life around the dead remnants of a massive star. It's still a little unclear how pulsar planets form, and only a few other examples have been found, but most likely they form out of the debris left over at the end of the star's life. When a collapsed stellar remnant is between 1.5 and 3 times the mass of the Sun, it collapses to an exotic state of matter that's essentially pure neutron material. The density of this is the same as that of an atomic nucleus, but with an atomic number of 10 to the power 54. Neutron stars were predicted, and for 3 decades, nobody expected to be able to observe them, until the accidental discovery of pulsars, the subset of neutron stars where cyclotron emission produces radio waves that sweep across radio telescopes with the spin rate of the neutron star. Several thousand pulsars are known, and they're representatives of the much larger unseen population of neutron stars in the galaxy. Spin rates can be as extreme as 600 or 700 times per second, and the magnetic fields exceed 1 trillion Gauss. These are truly extraordinary objects, the size of a city, but with the mass of a sun.